So I want to get rid of this. So I probably, okay. So welcome everybody. And this lecture is about how we can deal with systematic uncertainties in physics measurements using machine learning techniques. Now, I realize that most of the audience comes from data science and not particle physics, while this lecture will be focused on applications of machine learning techniques to and suitable for particle physics measurements. So this will be a very restricted domain where we will apply some of the techniques I will discuss. I think there may be a lot of technicalities that in these slides that I will try to avoid discussing with you. I will rather try to give you the big picture of how physics measurements, that is what we are doing, that we have lots of data that we get from these particle physics experiments. I will describe very quickly what I'm talking about. And we do inference, statistical inference with them. We extract information, we extract summaries, we extract measurements of physical quantities that we are interested in. And these data sets are affected by imprecisions, imprecise modeling, and so they have systematic uncertainties that we must deal with. So this is the problem that we are going to discuss today. And so the abstract of the talk is on the impact of nuisance parameters. That's how statistician calls a systematic uncertainty, because it's a parameter one is not interested in, but that affects the inference process, right? And we will focus on supervised classification, which is a very common and very wide-ranging techniques that are used in particular in particle physics. That's my domain knowledge, my domain of research is from this area. And on the techniques that we use and that we have been developing, and that may be special also for a data scientist, this might be kind of a niche application. So, but they may be interesting to you, I think. And these techniques will mitigate the effect of these nuisance parameters and their not precise knowledge in the information extraction procedures. So the approaches we will go over include models that try to parameterize these unknown parameters in the features that we use for the information extraction. And we will also discuss hacking the loss function of neural networks to include this effect by penalizing the loss or by constructing adversary setups. And we will also look at the forefront of this research, which is in techniques that try to inject in the loss function of neural networks some knowledge of what is the final purpose of our research, such that the machine learning tool can better align its output to our task goals. Okay, there's a lot of technical things in these talks, also because I designed it for a slightly different audience than what you are today. But so I will go quick on some of them. The slides will be made available to you. So if you want to go over them, you will have a chance to do so. Also, there's an extensive bibliography for those of you who are interested in the details that are given at the end of the slides. So, what is the impact that nuisance parameters have on particle physics analysis, and how can we reduce this impact? We will focus, as I said, on supervised classification. Also, regression is the same thing. We have a continuous rather than a discrete target, but most of the discussion applies there as well. But we will focus on a few specific examples that imply that we search for new particles, new phenomena that we try to put in evidence in these large data sets of particle collisions. There is a paper I have recently produced that will be part of a book on machine learning techniques for energy physics. And this is the link, and it's also in the reference section. So most of what I will be saying today, you can find it in this document. This is the contents of the lecture of today. I need to give you a very quick brush off of what is that we do in particle physics experiments. And then we will discuss the problem in a formal way, and what are nuisance parameters in statistical inference, what is their impact and how they propagate through uncertainty in our final measurements. And then we will try to look through the methods that have been developed mostly by physicists and also by collaborations of physicists and computer scientists to attack this problem, to make create statistical summaries that are robust to effect of nuisance parameters. And there's a number of them, as you see. So we will go quickly through these. But first, particle physics. So this is a cartoon of a collider enclosure, and okay, this is the typical setup of an experiment in particle physics. You have a tunnel, there's an accelerator, and we collect the data from particle detectors. So let's go through this in a very quickly. Okay, so we base our knowledge of particle physics in a model that we have constructed through tens of years of investigations of particle collisions. It's called the standard model. It's a full-blown theory which works extremely well. If you are familiar with modeling issues in various domains, forget it. Our model is incredibly more precise than any other model that you can think of, although we still have uncertainties, but at the level that still can affect our statistical inference that we use this model for. So we have matter. This matter is made by quarks and leptons. These elementary particles form nuclei of atoms, and the electron that rounds about the nuclei. And then there are forces that are electromagnetic. The photon is the carrier of the electromagnetic force. And then there are weak bosons. These were discovered in 1983 at CERN, and the gluon that keeps together quarks inside the nuclei. And there's a Higgs boson, a particle discovered in 2012, which is an additional peculiar particle that gives mathematical consistency to the whole construction. So we have the model, and we want to use it to look for something that the model doesn't include. So we will do hypothesis testing to see whether this model breaks down typically. But we will also make measurements of quantities that parameters of this model, okay? And we do this with a machine that is a giant collider constructed 100 meters underground near the town of Geneva in Switzerland. And this is a tunnel of 27 kilometers instrumented with superconducting magnets that allow protons to circulate in both directions and get to collide at a rate of 40 million times per second inside the core of the CMS and Atlas detectors, the two main particle detectors that are huge. As you see, a man here is standing here. These are little shot at than a football field as a size, and they measure and take snapshots of all of the particles, and there's thousands of them that get produced 40 million times per second when protons smash one against the other in the center of the detectors. Okay. So here are pictures of CMS, the detector and the experiment I worked for. It's a 7-story high thing, and it is comprised of hundreds of millions of electronic channels that read out the ionization and the trails and the light produced when the particles interact with matter. Okay. And we make sense of all of this by pattern recognition and then construction of high-level features that we then milk out in search for measurement. This is a cutaway view of a transverse slice of the CMS detector that you see here small. You must imagine that the beams of protons enter here in the slide, in this point, and then we have only a sector of it here blown up, and the scale in meters here. And you see that we have a tracker that can track the charged particles here with silicon detectors that are very precise. And then we have instruments called calorimeter that detect the energy of all the particles. And so we can detect whether a particle is an electron or a muon or a photon or a jet, and we can make sense of the whole thing. So we reconstruct these particle signals and we get these nice electronic pictures of the collisions, and we see sprays of particles that we call jets that detect the fact that the quark was emitted, kicked off of the proton by an energetic collision, and other particles. And then we can reconstruct these signals, and what we see, typically we make a mass distribution, a distribution of the mass that a particle would have if it had decayed in some other particle that we measure. And so sometimes these particles resonate and produce a signal that you see here as this Gaussian peak. It's actually a Bright-Wigner or a Lorentzian distribution, that you see that it's an enhancement in an otherwise flattish background distribution. So we look for these peaks in this data that are the black dots here. And you see that our model is a very precise model of the data. And sometimes we see a peak, and then we can reconstruct the mass of the particle that produced this peak and measure its properties. So what we do is a huge dimensionality reduction, because our data is really both tall and wide, in the sense that we have hundreds of millions of features, and then we cook up only tens of features, and we look at some of them through histogramming, okay? And we do inference only on these final histograms that we collect. So what do we do with these histograms? So we look for new particles, new physics processes that the standard model does not predict. We want to look forward and beyond, right? So there might be new forces out there, new matter particles. And we also measure the particles that we know about by doing precise determinations of the probability of particle reactions. So what we do is that we make extensive use of hypothesis testing and point and interval estimation. And you know that interval estimation, the sizing up of the uncertainty on a point estimate, is really, really the most important thing that a statistician can do, in the sense that understanding the properties of your measurements and how much you may be wrong in an estimate of a quantity that your data provides is really, really what is most important. In our analysis, so we do this very extensively, and we use lots of machine learning mainly to do dimensionality reductions, as you saw, to get to a small number of features, or even only just one feature, to select these very small signals in huge backgrounds. So in particle physics, the issue of selecting signal from background is central. And with the signal, then we do interval estimation, okay? So classification, supervised classification with machine learning. So here, for instance, you have a diagram. You won't make sense of it, but this is what is called a Feynman diagram that says that there are two protons that hit each other, and they produce a Higgs boson, and then this Higgs particle may decay and produce two energetic photons. And we measure the photons in the detector, and some distribution of the mass of the two photons has a small bump at the mass of the Higgs boson. That's how we discovered the Higgs boson. You see that the signal is tiny and the background is huge. Okay, so we have Monte Carlo generators that model the signal, and these Monte Carlo generators, of course, are affected by imprecisions. So we do a test of hypothesis sometimes to derive the probability of seeing some data given some null hypothesis or some alternative hypothesis. And this allows us to declare, aha, I have seen a signal here, because the probability that the data only conforms to the background is very, very small. So I am legitimated to say that there is a Higgs boson that contributes. And if I subtract the background I expected, I see a peak. If there is no signal, then we can do something else, which is we publish the search and we say we didn't see a signal. So if the signal was there, then I would have seen it. So I can exclude that the signal exists. And this we do it as a function of a parameter, typically the mass of the particle that we were searching for. But let's forget this, okay? So let's discuss more in general the problem that we have today. Supervised classification is used to construct a low-dimensional summaries. So we do it. We get summary statistics. What a summary statistic is a number, typically, or it may be a low-dimensional vector that can enshrine all the information that you want to extract from the data. And you can use these to carry out statistical inference on some parameters of interest, which we will call theta. So we can use a neural network to reduce some features, a vector of features of the events, maybe not 100 million, but maybe 100 variables that we have cooked up after doing some pattern recognition of those 100 million electronic channels. And we convert this into a single dimension output X, let's say a number from 0 to 1, which according to our model distributes with a certain PDF, which depends on the parameters we want to measure. This compression from Y to X is informed by simulated observations produced by some simulation, what we call the Monte Carlo simulation, a generative model. And this is, of course, a limited fidelity instrument because it may be imprecise. Let's forget what this means because you're not physicists. The detector that collected the data may be simulated imprecisely. We may be uncertain in the value of some fundamental parameters that affect what we see. And the data that we have is large, but maybe not infinite, okay? So all of these imperfections will be referred to as nuisance parameters. They can affect our extraction of information on the parameters of interest theta. So we can enlarge our model to include these nuisance parameters, alpha, a vector of unknown values, okay? And we can then construct a likelihood function with this enlarged model. So this allows us to account for the variability of the nuisances in our inference process. And of course, having included nuisance parameters, we will get enlarged intervals for our estimated parameters because we get a less informative output, right? Because we have smeared out our model with these alpha parameters. So we reduce the power of our inference in general. And this applies to high energy physics, as I've said, but the problem is, however, much more general, and it applies to any inference procedure that you may do, even in a totally different domain, because, you know, all models are wrong. All models are imprecise, and therefore there are nuisance parameters, and you must account for them. But better than accounting for them, it would be to disentangle from them to get your inference to become robust to the effect of nuisance parameters. That's the topic of this talk. So, parameter estimation, there may be nuisance parameters, their PDF may be unknown. What do? We cannot construct a likelihood if the PDF of the uncertain parameters is not known. So we can still try, okay? So Bx, our observations, random, identically distributed, independent variables, and theta, the parameter of interest, and we have some nuisance parameters alpha. We can still write the likelihood function as a function of alpha with this probability density model, and let it be certain that we may have only a hunch, not a clear model of what the effect of the probability, the alpha is on the PDF. So the likelihood is imprecisely constructed in that case. What can we do if we have, so typically what we solve the problem with is by finding the maximum of the likelihood with respect to the parameter of interest. So we get estimators for the parameter of interest by this formula. In the presence of nuisance parameters, we can act by constructing what is called the profile likelihood. And the profile likelihood is constructed by maximizing over the nuisances alpha by constructing the superior for any value of theta. And then this becomes only a function of theta. We have profiled away by taking the maximum this effect on the nuisance parameters. And then we can proceed as above. And there are techniques that have been published that allow you to do this rather seamlessly, okay? But this assumes that the likelihood is differentiable and is an impractical solution in large dimensional situations. There is also a Bayesian solution that allow you to marginalize over the nuisance parameters, but this requires you that you know the PDF of the nuisance parameter. And even then, nuisance parameters will affect the inference by widening our confidence intervals on the parameters of interest, okay? Okay, so this is how we deal typically with nuisance parameters. How about getting robust to their effect? We must know that machine learning applications usually focus on the goal of minimizing the statistical uncertainties on the estimates of the parameter of interest. And I emphasize the statistical uncertainty. The summary statistic that machine learning tools provide, like the output of a neural network, should enable the extraction of the highest amount of information on the parameter of interest, conditional to the validity of the underlying model used to generate the samples, as well as of the assumptions made on the value of nuisance parameters. So there is a conditionality here, okay? And the conditionality is very hard to get rid of. Of course, you would like to get rid of, but you can't, because problems are high-dimensional, nuisance parameters have unknown PDFs, and it is not easy to parameterize the effect of these nuisances, even if you knew their PDF. So all of this implies that the summary statistic is not usually sufficient. It doesn't know about a part of the feature space parameterized by these nuisances, and it does not retain all the information that is relevant for the parameter estimation task. It becomes liable to be outperformed. What is statistical sufficiency is written down in this slide. There's a Fisher-Neyman factorization criterion that tells you whether a statistic is sufficient. It is sufficient if you can factorize the PDF in this way, but I won't spend much time because you probably know about this, okay? The data of original data itself are a sufficient statistic, but okay, but it doesn't reduce the dimensionality. It's usually high dimensional. So what we want is a summary, okay? And if we summarize, we want sufficiency, but the sufficiency is hard to get. In practice, if we don't know the PDF in closed form, we cannot solve the problem analytically. But sometimes we can take tricks. So the density ratio of signal and background as a function of your variable of interest can be a sufficient summary for when your only problem is estimating the fraction of signal in some data set. You know, this is classification of signal and background. If you only care about the signal fraction, this may be a summary statistic. So probabilistic classification is a good way out in this case. Now, maybe I'm speaking to the wrong audience now, but if you read the literature of research in physics, you often read the word optimize. Okay, we optimized this search, we optimized this classifier, and so on. This word is used quite liberally, usually because people want to brag about their new classification method being better than not having been used by other colleagues before. But this is not really an optimization, because typically what they talk about is statistical optimization, but they don't deal with systematic uncertainties, because that's really the rub, the difficult part. Typically, what the evidence will be in support of an optimization task is that they show that the value of the area under the curve, where the curve in question is the receiver output characteristic, which is a function that describes the acceptance of some signal as a function of some cut at a fixed value of purity. We will see what this is in a moment, because I will give you an example. So the maxima of these proxies, like the area under the curve, track the minima of the statistical uncertainty on the parameter of interest, such as the signal fraction, but then they are oblivious to the fact that what we do with the signal fraction of some data is to estimate some parameter, a cross-section for some process or some other things that we want to measure. So they are an intermediate product, not the final one. And so if we optimize on an intermediate figure, we are not optimizing for our global task. And typically when we finally get our final measurement on the parameter we want to measure, we have to include the effect of systematic uncertainties, and this our classifier knows nothing about. Let's take a trivial example. So let's have a signal density that is this simple kind of exponential shape, normalized properly between 0 and 1, and the background will be another kind of exponential, which depends on a parameter alpha. Both these are normalized density in 0, 1, and we can label class S as y equal 1 and background as y equal 0, okay? So we have a background distribution which is uncertain because it depends on the value of alpha, which we don't know. Let's assume that we may know its value with some uncertainty, okay? So the task in our toy problem is to estimate the signal fraction in some data that we sample from the mixture of signal and background. So we want to train a classifier to distinguish the signal from background so that we can extract a better measurement of the signal, which typically is small as a fraction in this mixture model. And then we have several definitions for the true positive rate, the false positive rate, the area under the curve, and the rock curve. So the TPR and the FPR are defined as integral in what is called in statistics a critical region. So the data that passes a certain threshold on the parameter X, the output of your classifier. So if you look toward the right, towards the high values of the classifier, you will find signal, and you will have a true positive rate as a function of the cut that will be given by the integral of this distribution. And the same will be the false positive rate as a function of X star. Okay, and I've taken the effort to derive these analytic distributions here for you. From these, you may derive an expression for the receiver output characteristic curve, which is this analytic form, which, as you see, depends on the value of X star, which is the FPR of X star, but it depends on the value of this nuisance parameter. And the area under the curve is the integral of this function over X star in the full range. So it tells you that whatever the value of your cut, you are discriminating as well as possible. So here is the densities of background and signal in our model for three different values of the nuisance parameter alpha. And on the right, you see that extracted the true positive rate as a function of the false positive rate for the three cases of backgrounds. And you see these are the rock curves. And you see that the green curve is higher than the others. So it has a larger area under the curve, of course, because the background falls down more sharply. And so background and signal are better discriminated, can be better discriminated in this case. So what? Of course, if we train a classifier with a given value of the nuisance parameter, say 1.5, the performance of the classifier is going to be under or overestimated if the true value of alpha is different. So you are not doing the best that you can in discriminating if you have an uncertain value of alpha, okay? Your model is imprecise. Now, the fraction of the data that is selected in the critical region is the summary statistic in this case. It is our only input in the extraction of the signal fraction. And it is affected by alpha. It is not a sufficient statistic in this case. The whole distribution that you get would be a sufficient statistic because it would track the value of alpha, but it would not summarize our data well enough. And okay, and then we can derive a significance of some data that you select at values of x larger than your cut value, that you can write down as the number of signal and background events that you capture by cutting on the value of x star, plus some regularization value. So this is an empirical formula that works well and gives you a sort of statistical significance of observing a number of events ns plus nb when you only expect to see nb. This is a counting experiment where you look for an excess of events over a certain background model alone. So I made an example with where your model predicts that you see 400 events at a certain cut of the classifier output, and you have in addition 20 signal events. Okay, and let's see what happens for our significance figure of merit. You see that as a function of the cut on the selection of the data, depending on the value of the nuisance parameter, you get different value of significance, of course, because the nuisance parameter may worsen your discrimination. But not only that, the optimal value of the cut that selects the best significance in the model depends on the unknown value of the nuisance parameter. So standard supervised classification techniques may not reach optimality unless they know about the value of the nuisance parameter, because you may decide to cut at 0.38, but you are wrong. You are not doing the best because, in fact, you are suboptimal because the value of the nuisance parameter was different. Okay, so this is a problem, and we want to address it. How to address it? We can try to parameterize the nuisance parameters in the model so that the neural network or the boosted decision tree, whatever you have, will be sensitive to its value and try to be robust to it. So you can inject some a priori knowledge of the PDF of the nuisance parameters. Sometimes you can do it, especially when the dimensionality of your data is small. You can try a fully analytical solution to your problem in this case and decorrelate the effect of the nuisance through your classifier. So now we plunge into the physics, and of course you don't know collider physics, so I will just brush over this, but there's an example in this article that that discusses what is called wide jets. You see, this is a jet of hadrons seen by the CMS. The three smaller jets, because this is a particle that's the top quark that decayed into three subjets. So we have some features of these observable events that we collect that tell us whether this jet of particle is actually three subjets or not. So one of these variables is called tau n. Some other variables is called CLR, but they discriminate the production of a very heavy object, which we are interested in tagging, in observing, such as Higgs boson or top quarks and such, or even more exotic particles. And in this article, what these people did was to parameterize some of these important selection variables such that by cutting on this transformed variable that decorrelated the effect of the nuisance parameter, which in this case is a variable called the transverse momentum of the jet, would affect the observable variable which we wanted to study. You see in this graph, this is called the mass reconstructed for the particle which we search for. And we would like this distribution to not be affected by a cut on the discriminating variable. And instead, as you see, as we cut more and more, this distribution changes shape completely. But if we decorrelate the effect of this nuisance parameter, we get a distribution which much less sensitive on the value of the cut. And you can see this, I will cut this short because you are really not interested in what is called this boosted jet searches. But you see, this is a signal of your particle, which is a Gaussian bump, this purple one, over a certain background which has a certain shape. And if you uncorrelate the effect of your nuisance parameters, you get a much better situation where the background is much more flat, so its uncertainty will not affect your estimate of your signal. And you see it because the model here, the total model is in blue, and its uncertainty has shrunk considerably after you parameterize the effect of the nuisance parameter. Okay, so the typical problem that we have is that the data contain information on the nuisance parameters. So while we might in some cases get away with factorizing this nuisance parameter away and only consider the ratio of the density of signal and background and be happy with that, because if we have a model which has the likelihood written as a function of the parameters as a product over the data of the signal fraction times the density of signal and the 1 minus that signal fraction times the density of the background, this is called a mixture model. In this case, which is very common in particle physics, you can typically factorize away the background PDF, and you get to only have to study the ratio of the PDFs of signal and background, and these may have a better behavior with respect to the nuisance parameter. But if you do it, you will neglect this part, which contains information on the background alone, and you are throwing away some information. So this trick of only considering the ratio of densities reduces the amount of information that you can extract from the data. There's a paper that discusses how you can use summary statistics for the variables of interest and also for the nuisance parameters separately, and then you can get approximate sufficiency by doing this trick. But this procedure has not been tested, and since you are not particle physicists, I think we can skip this. Okay. And also, many times we don't know the value of our systematic uncertainty. We may not know the miscalibration error of our detector. We only have a hunch. So we don't know the PDF. We don't know its value. Or even worse, we are often in the situation where we search for a new particle and we don't know the mass of the particle. So imagine that you are trying to separate signal from background, but you don't know what the signal PDF is because you don't know what the mass of the particle is. You will try to create a discriminator that works well at a certain value of the mass. But if the mass is different, then the classifier will not work very well. Okay, it will degrade its performance as your signal model becomes different. Okay, so although the mass of the particle is actually something you're interested in, typically it's a nuisance parameter in a construction such as this. What you can do is that you can train many different classifiers using data that are simulated at different values of the mass. You can do this because you have a model for the signal at different values of mass, but you don't know the mass, so you will have to create a mixture of all the possibilities. But this is suboptimal because it also loses performance for any mass point, and also you use if you do separate hypothesis testing every time using a different classifier, you will only employ a fraction of the data in every case. So you are not making a good use of your simulated data. A better solution has been explored in this paper, which parameterized the effect of the mass of the particle, so the different properties that the signal has due to the different mass of the particle in the classifier itself. So if you do that, the classifier becomes more intelligent, okay? Of course, with the background, which doesn't know about the mass, it's not a parameter that affects the background. You must know what to do with the background in the training phase. So you might draw a value of mass at random for that. But okay, at this point, the network will be able to classify your events regardless of their mass, and also for mass values which the network has not seen before, because it has learned to classify at different masses, if you want. So this was done by enlarging a neural network model by adding these nuisance parameters, as you see in this sketch here, and you get an output of the neural network, which also has the mass as one of the parameters. You see here a background model and different signal models for this example, a search for a new particle in Large Hadron Collider data. And you can see here the area under the curve that these guys obtained for different values of the nuisance parameter. And you can check that, a network that was only trained at a specific value of the nuisance parameter, 1000 here, obtained a large value of the area under the curve, very good. But that a network that was parameterized to include the value of the nuisance was able to obtain the same area under the curve, but it could also obtain a much better result when applied to different mass values, while the network that had been trained at 1000 GeV did not work very well if it was to classify values of mass that were significantly different. Okay, so this is a technique that can work if you can pull it off. Sometimes you cannot, in fact, I will skip this because it's a bit too technical. Sometimes you cannot parameterize. So what do you do if you don't have a good way to parameterize a nuisance parameter in your model? You can do three different things that have been tried with various successes in particle physics analysis. One of them is to operate some pre-processing of the data to reduce the dependence of the classifier score on the nuisance parameters. Or you can construct some robust optimization objective for the classification task by writing down a loss function which knows about your objective and penalizes the values that are too sensitive on the nuisance parameter. And you can do this also using adversarial neural networks, which can achieve that same robustness that we just said. Let's look at it very quickly at some of examples of these methods. So mass decorrelation is called because we are particle physicists, we are interested in the mass, we want to be decorrelated from the mass that we measure in these events, the mass of the particles that we reconstruct. This is because we are looking for a small Gaussian signal, as you saw at the beginning of this talk, over a flat background distribution of the mass. And if that background distribution is changed by cutting on a discrimination on a classifier output, then you are in trouble because your inference on the resulting distribution will be very sensitive on this mismodeling of the background. So you want to decorrelate the distribution of the mass from the output of the classifier. And one way to do this is called planning. And it's a very simple idea. You preselect the training samples for the signal and the background such that they have the same density function on the variable that you want to decorrelate against. because if you reweight the signal and background such that they look exactly the same along that marginal variable, then they will be insensitive to this distribution. But this only works to first order, and it's also suboptimal because you are also selecting your data before you train. That is, you make less use of your data. A better strategy is to reweight each training event by a weight which depends on the probability of seeing that value of mass or of the planned variable. So you make optimal use of the data this time. Planning is actually an effective way to decorrelate the effect on some nuisance variable. And it is only limited by the fact that some other event features will indirectly inform the classifier of the value of the planned variable, which may have some discriminating power between signal and background. In fact, it has typically high discriminating power, and you were trying to wash it away a little bit by planning, but this only works in part. This is one example. You can, in this article, they try to do principal component analysis on some event features before they train the classifier. And they showed that as you go from the top distribution to the ones below that are obtained as you cut more and more on some discrimination variable, you see that the background remains of the same shape, which allows the signal to stick out more and more, irrespective of where you trained, whether you trained for the signal at some mass or some other mass. So this becomes an effective technique. And there are other methods that use to write down a penalized score. So one of these is based on a modified boosting scheme. You may be familiar with ADA-boost, which is the technique originally implemented in boosted decision trees, which increases the weight of previously misclassified events. And this U-boost technique is a hacking of this technique, which includes a factor which takes into account the fact that you want to keep you don't want to bias some variable and keep a selection efficiency that is uniform. In this case, in a plane of two variables, this is called the Dalitz plane. Before we were considering only the mass. Here we are considering two variables on which you want to retain a uniform efficiency. And these guys have cooked up this method. And okay, I don't want to explain to you what the Dalitz plot is, because it's really a technical information about particle physics. But you have a plane of two variables, and the background wants to be distributed uniformly in this plane, such that you can see structures that is your signal in this plane. And these U-boost techniques can actually do this for you. You see that this distribution on the right is much more uniform than the original one, because this U-boost technique has been able to select the data without affecting the efficiency with which the data is retained by the cut on these two variables. I guess yeah, there was somebody to admit in the room. I will skip this, which is a further development of this technique, which is only relevant to some particle physics analysis. I don't think you are very interested in this. There's another technique that penalizes the loss function of a classifier by adding with an hyperparameter lambda what is called the distance correlation between two variables. And this is defined by a ratio of covariances of two sets of variables in a batch from the two different categories of data. And it is the value of this is that it is a differentiable function computable with data samples, and you can include it in the loss function of a classifier, such that by tuning this hyperparameter lambda, you can decorrelate the effect of the nuisance parameter from the output of the classifier. And this is a nice example. You see, this is on the left is a distribution of the signal that you want to evidence, and the background in blue here is again as a function of what we call the mass of the particle. Okay, so you want to distinguish these two distributions, and the fact is that any classifier will learn the signal distribution in the mass if you give it enough information and in many other features. So you see that the background will distribute after the cut with this red distribution. It's very annoying because now the background has the same shape of the black signal on the left that you want to discriminate against after the cut, right? Okay, you have increased the signal to noise fraction by cutting on this discriminator output, but then the background becomes exactly equal to the signal. Instead, if you apply this disco penalization, the background after the cut, you can see this in black, has remained exactly equal to the original one in blue. And so you still have discriminating power in this variable, which is giving you the chance of producing a nice money plot where you can see an excess which doesn't behave like the background in this variable, which for physicists is very important. The mass is something that has some meaning. It's an attribute of the particle, okay? And there are ways to compare how much you can decorrelate this on the vertical axis. This is the inverse of the Jensen-Shannon divergence between the background before and after the selection. And is plotted here as a function of the background rejection, which you want to be as high as possible. So here in this graph, you want to be on the top right of the plane. And you can see that many different technologies for separating signal and background and trying to produce the correlation act differently, produce a larger decorrelation, but a lower background rejection. And you can see here, you can check that this DISCO, distance correlation technique, can do a decent job. And you also see that the planning is actually doing a very good job as well. So it's a very simple technique that works well in this case. Other penalization schemes have been studied. I won't have time to discuss them. But here you have an example where you have a signal here and backgrounds that can be here or here or here, and a classifier that doesn't know where the background sits will produce isolines of discrimination that are diagonal. But then if you can sort of rotate away the nuisance, you get discrimination curves that optimally distinguish without being sensitive of the value of the nuisance parameter, which tells you where the background is sitting on this two-dimensional distribution. So you get smaller uncertainties on the distribution of signal and background. Okay, but I'm going in too much detail here. There's adversarial setups. Now I'm talking virtually in Russia, so I take the liberty to have a slide about the national game here. This is actually a chess problem I composed where you have to apply backward propagation to solve it. Here, white to move wins. But okay, I'm not diverging because, you know, to create automated programs that play chess, you have to apply a minimax routine, which is basically trying to maximize the advantage of the position of the player that has to move, irrespective of whatever move the opponent does. So this is a minimax, okay? And it can be solved by adversarial setups. In adversarial settings, you also have a loss penalization, and they are more symmetric setups. So I left them distinguished from the previous discussion of loss penalization methods. By the way, if you want to solve this problem, send me an email and we will discuss. But okay, adversarial setups are typically investigated in computer science, and you know this well, to achieve domain adaptation, because you have training and test data that come from different PDFs. So it's typically, you can describe this as having some nuisance parameter, okay? So you want to find the data representation that is maximally insensitive of their source. And you task an adversarial neural network to learn such a representation. while competing with the task of separating the labeled classes. The first use case in particle physics of an adversarial user neural network was developed in these papers, and they came up with a setup that they could show worked well for finding new particles. This is their setup. You have a discriminating network and an adversarial that tries to distinguish values of the nuisance parameter, and you pitch one against the other. This is the algorithm, and this is a similar setup to the one we already discussed, where you have background that sits at unknown values along the y-axis, and again, this adversary can rotate to a vertical line, the isolines of different discrimination power, okay? And this is a high energy physics example to this, to which this has been applied, where you see that some maximum significance of a selection cut, this is the cut value, is produced by some value of the hyperparameter that models how well, that decides how much importance this decorrelation has to have with respect to the classifier loss. And you achieve a good result in this case. I want to discuss what this physical example comes from, but if you really want to know, this is discriminating signals from backgrounds in a case where you have large number of collisions that create noise in your detector. Okay, this is a common problem in particle physics at the LHC, but not to your interest. And there have been further developments of these adversarial setups. This is a particle search where the neural network output depends on this nuisance parameter, but after pivoting through an adversary, you see that the black points are insensitive to the value of the mass, and so you get the chance to classify with a higher power and higher signal efficiency and higher discovery significance. I am probably running out of time, so I will skip these further developments along these ideas that I discussed. Also, they are probably not of much interest to you, but if they actually are, you have the references here. There's a whole class of other attempts that try semi-supervised approaches to deal with nuisance parameters. And they try to close the gap between learning from simulated data and real data, where, okay, the domain adaptation problem is again on, okay? These methods, however, rely on assumptions themselves, and these are hardly met in practice, so they have a limited applicability. One case is called learning from label proportions, that substitutes a loss that knows about the labels of all the training data with a loss that only knows about the average label of some data. And you can still learn, and you can still train a classifier, and you can still get decent, actually perfect results compared to full supervision if you have samples that have different label proportions to train from. And so, okay, in this particular case, you can work well. And it has been tested on some model where you had some imprecision in the simulation, so that when you consider this nuisance parameter, full supervision is actually doing worse than weak supervision because it is more sensitive to the nuisance parameter. And there's another attempt here that's called the classification without labels that actually gets rid of the label proportions, but it only cares about discriminating based on the fact that you have samples that are different in the fraction of signal. And you just use the identifier of the different mixed samples as labels, and you can still train, and you can still obtain a very good classification performance. And the algorithm does require that you have labeled the data for tests of performance and choice of operation point, but the proof of principle shows that you can actually work with this. So you get rid of the idea that you know the labels of the data, but you just have data sets that have different signal proportions. And finally, there are inference-aware approaches. Unfortunately, I'm running out of time, but this is the most interesting part, and the one that also for a data scientist should be the most interesting. Excuse me. So these are solutions that try to move away from the proxy classification task, which, as we said, is an intermediate step, and try to address directly the task of optimizing the final product that we want to achieve. So having the smallest uncertainty bars around my parameter of interest measurement, okay? This is really a realignment of the task and the objective. Here I want to just browse quickly through some of the ideas. So there's a whole class of papers that have been published on this idea to augment the training data with information from the simulation to learn more efficiently from the simulator and do what is called likelihood-free inference in a more effective way. But it's a big topic for another lecture, okay? What is inference-aware summary statistics? That we must go back to understand this. We must go back to the typical procedure in high energy physics, which is we have a sample of data that is signal and background. The signal may depend on some parameter we want to estimate, say theta, and we have some uncertainties. But we don't care about the uncertainty systematics. We optimize the classifier to distinguish signal from background, and we choose the operating point to have the best possibility of discriminating the signal, such that you can measure the parameter theta as well as possible. And then you parameterize the shape of the classifier as a function of the cut, you fit for the signal function, and then you account for nuisances as variations of this shape. But you see, when you do this, the classifier has already learned its task and it can't be changed. So, you have bypassed it and you cannot get back. You can also, in any case, when you do this, basically you are doing something suboptimal, okay? You have misaligned your task to your real goal. So we must inform the classifier of the effect that nuisance parameters have on the final measurement goal. So how do we do that? One paper I published last year does exactly that. It makes the loss of a neural network aware of what we want to do with the neural network output. Simultaneously, it injects in the loss a parameterization of the nuisance parameters so that the loss can work with this full model to minimize exactly what is our target. And our target may, for instance, be the total uncertainty, not just statistical, but statistical plus systematic of the final measurement that we want to make. This is done within the AutoDiff framework of TensorFlow, but there is an implementation now done by Giles Strong, which works in PyTorch. So the TensorFlow implementation is in GitHub. You can find it through this link. This plan is difficult because you need to produce a differentiable map of the nuisance parameter effects on the features. So you have a multidimensional problem here. And this calls for custom solutions in energy physics problems, which are very complex, of course. But if you can pull it off, then you have another problem: how to estimate the final variance on the parameter of interest out of this full mixture model plus inference process. So you have to model the inference process. And what you do is you use the inverse of the Hessian matrix of a likelihood, which is constructed with the summary statistic provided by the neural network. What this means is that you create a model of how the uncertainty bars of your final measurement will turn out to be, depending on the output of the neural network, such that the neural network can tune to that. This is the framework. You see, you have a simulator that produces data, and then you have a neural network that produces some outputs that you can pass through a softmax operator to make this differentiable. And then you pass this summary statistic to a likelihood which you maximize to obtain some parameter of interest estimate, and also the second derivative of the likelihood, which will tell you about the variance of the parameter of interest that you get out of this whole procedure. And if you feed this information matrix back into parameters of the neural network, the maximization of the loss, the minimization of the loss will produce network parameters that will guarantee that you get the smallest variance. Here there are some details of the internal procedure, but I guess I'm out of my time. So you have them here, however. There's a paper for you to read if you are interested in, or you can send me email. The pseudocode is also here, but I basically described it already. So you have a gradient descent minimization that produces through this neural network this n-dimensional summary statistic, which gets fed after a softmax operation into what is called an Asimov likelihood, which is a saturated model where you use data that is exactly conforming to the model, so that you get the expectation value, if you want, of the variance out of this second derivative. But all of this is differentiable, so that you can do SGD and with batches of simulated data, and you can actually optimize the whole thing. Here you have a synthetic example that shows a signal distribution and a background distribution, and this actually in 3 features shows that you have the background that actually has some nuisance parameters that affect the position of the background and the shape and the exponential slope. So you can try to maximize the uncertainty, minimize the uncertainty on a parameter of interest, which may be the cross-section for the signal or whatever, with this setup. And you can test it and compare it with other approaches, and also compare it with the uncertainty that you get from a know everything analytical likelihood approach. And you see that Inferno actually works very well. It produces results that are that have uncertainties very, very close to the perfect ones. So the problem is that Inferno requires you to model these nuisances, and it's not easy to do. We have right now a PhD student that is applying Inferno to a real high energy physics analysis. So we will soon know what are the stumbling block of that. Sorry. And there have been recent developments of these inference-aware approaches by other groups of people that have basically built on the same idea in slightly different ways. And there's a number of papers that have appeared. And of course, this idea that you can inject, make the neural network be only an element of a pipeline where you let all of the elements of your problem know about all of the other parameters and maximize an objective function which knows exactly what you want to do with the input data. This is really the goal that we should set to ourselves in complex problems such as this in particle physics. So, in summary, I hope I have been able to give you a glance of the wide arsenal of techniques that have been developed and are being developed in particle physics to remove the impact of systematic uncertainties in supervised classification problems in the presence of nuisance parameters. Okay. The focus is typically the one of achieving the correlation of some significant variable And here you have seen many different methods at work, but I think that the real important issue is how to minimize the effect of systematic uncertainties by keeping in mind what your final target is. So it's a problem of alignment of your machine learning task with your final product. So I think this is an active area of research in machine learning, and in fact, the next steps of this plan of research involves work that is being considered in a collaboration, which we have now also with the Laboratory for Big Data Analysis of HSC and other institutes around the world that plan to create a machinery for full optimized design of complex instruments, such as those that we use in particle physics. Thank you for your attention, and I'm here to answer your questions if I have the knowledge to do so.